Good day, learners. Welcome to the discussion on the grade 11 mid-year examination paper. We are going to go through the geography paper for grade 11, and we are going to try to analyze the questions and try to give some justifications to the possible responses for the paper. Right. As usual, this is going to assist you in preparation for the other coming examinations, or for those who are in previous grades, it is going to assist you in preparation for the grade 11 paper. Right. The mid-year paper, as usual, we understand is out of 150 marks, and the structure is such that we have our theory section being made up of two questions. Question number 1 out of 16, question number 2 out of 60 again. Question number 1 based on the atmosphere, and question number 2 on geomorphology. And question number 3 is geographical skills and techniques. Right. We go to our questions. Right. Our first question is basically based on a synoptic map, and we understand our synoptic maps. Right. That is a map which gives us a summary of the weather conditions of a given place in a day's time. So by me looking at this map here, we can see quite a number of features which are evident on the map, which we need to validate and which we need to use in answering the questions. Right, for the sake of our discussion, we are focusing on the questions. The synoptic weather map above indicates, is it summer, spring, autumn, winter? Right, if we go to our map, we tend to find that if we check here on the dating of the map, we can see that the date is telling us that is the map for 2025, the 5th of June. And also, if we check on the position of this high pressure cell and this high pressure cell, we can figure out the season for the map. Right, for this reason, we are having our date June. We know this is our southern hemisphere. June is a winter month in the southern hemisphere. And also, these our high pressure cells, they are further to the north. When it's winter, they move further to the north, like they are to the sides of South Africa. But when it's summer, they are further to the south, somewhere here. So we have our South Atlantic high pressure here and our South Indian during summer season. But when it's winter, they are closer to further to the north. Right, so that is winter for our first question. This is a winter map. The lines on the map joining places of equal atmospheric pressure, those are what we call the isobars. These ones, the isotherms, they are for rainfall. They are for temperature, these ones. They join places of the same temperature. And these ones are for rainfall. Then the millibars are a unit of measurement of atmospheric pressure, or in other maps, we use the hectopascal. Right, then dash is the unit of measurement of atmospheric pressure, is the hectopascal, the HPA. All right, moving on. An area of constant pressure at sea, an area where there is constant pressure. We are saying the pressure is equal throughout that particular area. What kind of a geographical phenomenon is that? right? That is what we call a saddle. Then number 115, the change of atmospheric pressure from high pressure area A to a low pressure area B. What is that? A change of atmospheric pressure from high to, that is pressure gradient. The isobaric interval on the map, what we call the isobaric interval, we're looking at the difference in atmospheric pressure between two consecutive contour line isobars. Right, so we don't need to worry there because our units of measurements are already giving us a clue. 4 degrees Celsius is for temperature. 4 HPA, this is for pressure. This is height. So automatically our correct answer is B. You recorded the atmospheric pressure of dash at B. As you move towards A, atmospheric pressure reading changes and reach the high pressure reading of. Right, if you check here, um, we are comparing area B. This is area B and this is area A. Right, so what it means here is at B, our pressure reading, if you try to check in the mid of the low pressure cell, there is another isobar. This 992 is outer. There is another one inside, which is reaching B. So using our interval of 4 hectopascals, we are going towards the center of the low pressure. It means must subtract the interval to get the value of this one. So it's 992. We less 4 and we get 988 HPA. That is how we get this value of the low pressure isobar in the interior of at B. Right, then we are going outside, we are going towards the high pressure. We see our reading here is 1024, and this is not reaching the center of the system. It's not reaching the center of the high pressure cell. And we understand as we get towards the center of the high pressure cell, we expect our pressure to get higher. So we need a pressure which is above 1024. It must be higher than 1024 because we are getting towards the center of the high pressure cell. So automatically we are picking 1040. So we are saying the reading on the outermost part must be 988 according to the calculations. And in the center must be above 1024, which must be 1040. So response A and response number 1 and number 4, they are combined at option A. Right, moving on to question number 2, which is showing the situation of rotation and revolution of the Earth and also the situation of the equinoxes and the solstices. Right, the movement of the Earth around the Sun on its orbit around the Sun, that is rotation. The Sun rotates in 24 hours. The Sun strikes perpendicular at the Tropic of Cancer in which season? Tropic of Cancer. We know that our Tropic of Cancer is in the Northern Hemisphere. So for us in the Southern Hemisphere, we'll be in winter. So there's a distinction here. Tropic of Cancer is Northern Hemisphere, summer, and Tropic of Capricorn is Southern Hemisphere, summer. And the opposite is true. If it's summer here, it's winter in the southern. If it's summer here, it's winter in the northern. The arrow at A shows the Earth's, this A here. It shows the rotation. Tropic of Cancer is in the dash hemisphere. We've talked about that. Of Capricorn is in the southern hemisphere. Of Cancer in the northern hemisphere. Our Tropic of Capricorn ultimately apparently crosses through South Africa in Limpopo there. That is where we have our 23.5 degrees line of latitude to the south. It actually crosses through Limpopo. Right. The tropics are at the line of latitude. The tropics, they are at 23.5 north and south. That is where we have our tropics. Tropic of Cancer, 23.5 degrees to the north. Tropic of Capricorn at 23.5 degrees to the south. It is experienced when days are longer and nights are shorter. A situation when days are longer and nights are shorter, that is a solstice. In equinox, we are having a situation of equality in the number of hours between the day and the night. The atmosphere is heated more by terrestrial radiation, which is long wave radiation. Temperature dash with an increase in latitude. Temperature decreases with an increase in latitude. What are we saying here? Our latitude, we are referring to distance from the equator. We have our 0 latitude, and let's say we have our 30, and we have our 60 and 90. An increase in latitude, we are moving from the equator from 0 going to 90 north and from 0 going to 90 south. This is the polar region. It's freezing. So our temperature decreases with an increase in latitude. Right, refer to 1.3 showing the global air circulation. Right, we're having the situation here. Define the intertropical convergence zone, the ITCZ. Right, intertropical, meaning to say it's within the tropics. Convergence, meaning to say it's a belt where two air masses meet. So defining it in simple terms, we can say it's a low pressure zone within the tropical region. Where the tropical easterlies converge, or in simple terms, where they meet. So in simple terms, what are we trying to say? We are saying we have a zone of low pressure or a belt of low pressure that exists within the tropics. And the tropics, we understand we are looking at the regions between around 0 to 23.5 or 23.5 north and south, or to be more general, to the 30s. And in that belt, we have low pressure. And because of the low pressure, we tend to find that the tropical easterlies from the north and the tropical easterlies from the south, or the trade winds, they tend to meet in that low pressure belt or converge. That the ITCZ. Or we can say it's a low pressure belt where the sun is overhead. The sun is overhead position. That is what uh, actually clarifies the ITCZ. Because of the overhead position of the sun, we tend to have a low pressure developing within the tropics. And for that reason, there's low pressure and there's convergence of the tropical easterlies in that particular zone. Right, moving on. Identify the air circulation cell represented by the diagram. Right, we understand the tricellular model of global air circulation, if we still remember. The one which is from the ITCZ to the around 30s, we are seeing it here, which means from the ITCZ to 30, we have the Hartley. It's the Hartley, then the Ferrel, then the polar cell. Right, identify the winds blowing from 30 towards the equator. The moist air here, I think I've talked about that. These are subtropical easterlies. Or in other words, we can call them the trade winds. These are the winds that we are seeing here from the north to the south. The same winds here, they are the trade winds. Identify the pressure belt formed at 30 north and south of the equator. That pressure belt is the subtropical high pressure belt. There is high pressure here at 30. So basically we are saying in simple terms, to understand our diagram, we are saying this particular belt here at 30 is a high pressure belt, and the ITCZ is a low pressure belt. So for that reason, we are saying at 30, either to the north or to the south, this is a high pressure belt, and this is also a high pressure belt. And this one is now a low pressure belt. And for that reason, there's pressure gradient. The air is going to blow in this direction, and the air is going to blow in this direction. And there is convergence here. What happens when the two air masses meet? They uplift. And when they uplift, because they are moist, a cloud is going to form, which is going to produce rainfall. Describe the weather conditions associated with the winds identified at A at 3.1. What are the weather conditions? They are associated with warm conditions or warm temperatures. Because of the region that they originate from, they originate in warm conditions. They are featured by warmer temperatures and humid conditions. And we also have heavy rainfall. That's basically the weather conditions that we associated with the tropical easterlies or the trade winds. Right, then the last question says, explain the formation of the air circulation cell identified. I'll use the diagram to explain. Right, for the same reason that I was explaining here is the very same reason that this high pressure cell is going to develop. This circulation cell is going to develop. So this Hadley cell, when we're explaining the formation of a cell can form starting from any point because it's a continuous process. The process does not have a starting point and an ending point. Like you are circulating, you are running in a circle. You can start anywhere and you can end anywhere when you're tired. So in this instance, this is a continuous process. So our explanation can start from anywhere. Right. I'll illustrate here for the sake of what I want to explain. There's high pressure and there's low pressure. I will start from here and there's high pressure here. Right. There's high pressure on the subtropical pressure belt 30 south and 30 north. And there's low pressure in the ITCZ. So air because of pressure gradient moves from the high pressure subtropical belt to the low pressure ITCZ, and also from the subtropical high north to the ITCZ. The air converges at the ITCZ and uplifts. As the air uplifts, we have these conditions forming here. They don't matter, we want the cell only. The air reaches upper atmosphere. It has lost moisture and is cooled. After the air is cooled, it becomes denser and it sinks at around 30 degrees to the south or the north. As it sinks, it creates a high pressure Again, there's still a low pressure on the ITCZ. The air is driven by pressure gradient to the ITCZ. So at the end, it's a continuous process. It can start from the high pressure here of sinking air. The air is drifted by pressure gradient. It converges at the ITCZ. It rises. It loses moisture. It reaches upper atmosphere. It is cooled. It becomes more dense. It sinks around the 30 degrees. So that is how basically what you must explain there. Right, refer to figure 1.4, which shows phone winds. Define phone winds. Right, when I'm defining this, we must address the basics. Like, what kind of a wind is it? It's a hot, dry wind. And remember, this is a hot, dry wind, which is also regional. Which areas does it affect? Affects Central Europe. And how does it form? Formed through adiabatic heating of air descending the Alps mountains. Right, for that reason, I think you would have addressed the basic requirements. You have given the nature of the wind. It's hot and dry. And since it's a regional wind, where is it experienced? It's typical wind that affects Central Europe. How does it form? It is formed through adiabatic heating of air that descends below the Alps mountains. So it's adiabatic heating is the one that causes its dryness and its hot temperatures. Right. Moving on to the next question. I'll use the illustration here to try and simplify what we want to explain by adding some labels onto the diagram. Right. So we are saying in this instance, we are having the Mediterranean Sea here. Our Mediterranean Sea to this side. Then we have our Alps mountains. Then we have Central Europe on this side. And what is going to happen here is this air is going to rise here and is going to cool at a dry adiabatic lapse rate. And when it reaches, this is the dry adiabatic lapse rate. And as the air continues, this rate is 1 degree Celsius for every 100 meter. Then as it reaches the condensation level, the rate changes. It now cools at a wet adiabatic lapse rate. And the rate now will change to around 0.65 degrees Celsius per 100 meters. Then as it gets here, it's cold and dry. It now starts to heat as it goes down. It now heats up at a rate of 1 degree Celsius for every 100 meters. This side is now adiabatic heating. This side was adiabatic cooling. So basically, those are some of the illustrations that are necessary that we are going to use to answer the questions. Right, for that reason, we are saying, what is this temperature? It says as the air continues to rise on the windward side, the temperature changes at a rate of 0.65 per 100 meters rise. As it continues, that is the guideline. which means it's not the initial rising. As it keeps on rising, the rate becomes that one. So what is the temperature lapse rate called? So the lapse rate here is the wet adiabatic lapse rate, or what we call the saturated adiabatic lapse rate. At what rate will the temperature lapse rate not mentioned change? We have mentioned this one of 0.65. So what is required is this one, which is not mentioned here, the dry adiabatic lapse rate. That is 1 degree Celsius for every 100 meters. What forces the wind to rise on the windward side? What force is there is the mountain barrier. Because there's a barrier, there's a mountain, the mountain is going to force, or in simple terms, we can say it's orographic uplift that happens there. Because there is an orographic feature, it forces the wind to rise. Right. Briefly explain why the temperature on the windward side is 2 degrees Celsius and 10 degrees on the leeward. At the same altitude, at this altitude here, if we continue this line, it can perfectly meet 10 here. So at this, we are seeing is 2 degrees Celsius, and here is 10, but it's the same altitude, it's the same height. Why? It's because here the air is cooling. On the windward side, there's adiabatic cooling. And on the leeward side, there is adiabatic heating. That is why the temperature is lower here, it's because the air is cooling down. But as it's descending, the air is now heating up. So at the same altitude, we have different temperatures for that reason. Discuss the impacts of foehn winds on the environment. We said they are hot and dry. So what is the impact of having hot and dry air on the environment? Right, it is going to cause temperature increases. Which is going to influence local climates. Local climate conditions. The climatic conditions are going to be affected by the rising temperatures because this air is hot. So it's going to cause rises in temperatures in the areas of effect. And as a result, we are going to experience a situation of higher temperatures in those areas. So which gives us a negative implication on the environment. And also in Central Europe, is going to cause snow melting. And snow melting can have a positive impact. It can help in replenishing water sources. Then it can also facilitate drought conditions. Since it reduces humidity. Because of reduction in humidity, the air becomes dry. It facilitates dry conditions in the areas of effect. And also risk of wildfires or the wildfires. Because of excessively dry conditions, we have a risk of wildfires starting. And the other impact, we can also talk of impacts like ecosystem disruption. Because of excessively high temperatures, it tends to disrupt some ecosystems. And also we can talk of it reduces soil moisture. Dehydration, moisture stress on vegetation. Yeah, those are some of the effects on the environment that we can talk about. It can cause moisture stress on vegetation because of excessively high temperatures, and also dehydration is a typical effect on wildlife, and also soil moisture is reduced, which is also going to affect the growth of vegetation and also the productivity of vegetation, and apparently it's going to affect biodiversity for those reasons. Right. Next question is on desertification and the droughts, and an initiative to try and regulate the effects of desertification. In the Sahel region, we are seeing that there is the creation of the Africa's Ambition Green Belt projects. Right, we need to go to the question. Define the concept desertification. When we are defining this concept, we define it in most simple terms. Right, desertification coming from the word desert, we know what a desert is. So, when desertification is happening, what is the ultimate thing happening? Is the extension of desert conditions into areas that were once suitable for productive agriculture. That's basically desertification. We are looking at the deserts extending into other areas that were once suitable for farming. We know desert conditions are not conducive for agriculture. They are very hot and there's limited precipitation. So if those conditions are also extending, the soils are less fertile, they are infertile because we have sandy soils in the deserts. So if those conditions are extending into neighboring areas, that is desertification. Deserts are extending into the areas which were once suitable for productive agriculture. That is explaining desertification in simple terms or defining it in simple terms. According to the infographic, what is the main aim of the Great Green Wall project? Right, when we are using this, it's an extraction question. We just go to the extract and find the aim. The aim was to curb the Sahara Desert spread. Otherwise, we are saying the aim was to try to control the extension of the Sahara Desert into neighboring areas. That's the aim, according to the extract. Right, moving on to the next question. According to the infographic, what is the main cause of the rapid spreading of the Sahara Desert? Again, it's extraction. We just go to the source. The change in climate and weather patterns is triggering a rapid spread of the Sahara Desert. So that is extraction. Change in climate and weather patterns is the one that is triggering rapid spreading of the Sahara Desert. Calculate the temperature range in degrees Celsius between January and July. We need to come and check here. January, February, March. January is here. It's 5. Right. Then this is graph for weather and climate. And if we try to check and analyze there, the graph is showing us two extreme sides of temperature and rainfall. So our graph for temperature is the one which is graphs for weather and climate showing desertification. Right, so if we check on the graph here, we can see the reading for January, and we say check the reading for June. But the problem here is our readings, our graphs are not indicated the variables, whether we are using the line graph for temperature or we must be having another variable on the right-hand side showing, or we must be having a key which shows which graph are we using for the calculation of the temperature. But assuming that we are using these graphs here, it's an assumption that you read for the January, and also you read for the July temperature, and the temperature range is ultimately the difference between the two. You check the difference there between the two, and that is going to be the reading for the difference between the two readings of January and June, according to the readings on the graph. But unfortunately here, our graphs are not indicated whether this is the graph for temperature, the line graph, or the bar graphs, or which one is which. We must be having a key on the graph to indicate which reading is for which particular variable. Because since we are having two graphs here, we cannot ascertain which one is for temperature and which one is for the other variable, because there are two variables on the graph. Right. Name two human activities that contribute to desertification. Two human activities that contribute to desertification. We know that humans are also responsible for desertification, for the extension of deserts. So activities like deforestation, the deliberate removal of vegetation, is a factor promoting desertification. And also, if we look at poor farming methods, they also contribute. If you look at poor farming methods, they are also a contributory factor. And also, if we check, we have human-induced soil erosion. We lose productive land because of human activities that facilitate soil erosion. So we can ultimately attribute those factors to human factors that contribute towards desertification, how human beings also contribute towards desertification. Right, the next question says, in a paragraph of approximately 8 lines, discuss the positive impact that the Great Green Wall Project will have on people living in the region. Right, that initiative of planting trees, how is it going to impact positively on the people? Right, we can argue that there's going to be job creation. People are going to get jobs, e.g. in forestry, or in agriculture. People are going to get gainful employment. So it's going to be beneficial for the people. And besides job creation, we can also look at improved livelihoods. For example, income. People are going to get a decent income through that project. And also the effect of food security. People are going to be food secure for that project. And also it can assist in improved water availability. If an area is being threatened by desertification, it implies that the amount of water that is being received there is gradually declining. So with that project, apparently it's going to contribute towards sustainable rainfall. And also we can talk of other effects like it leads to sustainable development in the area, long-lasting development. The area will keep on developing because of that project. Right, so we can apparently argue on those reasons to justify the benefits of that project to the area. Right, question number 2 is geomorphology. The first question is based on this illustration of intrusive volcanic features. Right, forms when magma flows, erupts onto the surface and solidifies due to contact with the air. This is extrusive for outside features. Right, then the next question is talking about the features above are associated with which type of rock? Those are igneous rocks. Remember, igneous rocks are of volcanic origin. You cannot have sedimentary rocks forming those features. This geomorphological process is responsible for the exposure of the features above. The exposure is through erosion. One landform that may develop from feature A. From feature A, you can see feature A there. From the batholith, we can have a granite dome, which later is a dike. A dike, it cuts through the rock layers. So it's C. If you check there, our C is cutting through the rock layers. One South African example of feature B. Feature B, typical of the seal. We can relate that to the Bushveld complex. What valuable mineral could possibly be mined from solidified E? At E there, what can we actually mine? We cannot get coal there, we can get diamonds. Right, then question number 2.2 is based on this illustration again of features resulting from inclined rocks. Right, our first question is saying the landform illustrated at E. At E there, you're seeing where E is, this gently sloping landscape and steeper on the other side. Is a what kind of ridge? That is a homoclinal ridge. This landform forms because of these are inclined rocks. The distinguishing factor of Kester and homoclinal ridges is mainly the angle of the dip slope. Is the one that distinguishes how steep it is because of the angle of dip slope is the one that determines. Right, the number 1 on the diagram represents, if you check number 1, this side which is gently sloping, it's a deep slope. Then 102, slope of a ridge is not suitable for human usage. 102, 1 is gently sloping, 2 is very steep sloping. We cannot have human activities or human usage on 2. The rocks at G are hard or less resistant. At G, these rocks here, that will form the deep slope, right? Automatically, those rocks are hard and resistant. Direction of scarp retreat on landform E, is it eastwards or westwards of this landform here? Does it go this direction or this direction? It goes to the west. Scalp retreat is goes to the westwards. Right. Moving on. Letter G is likely to have developed from a right. Letter G, we are seeing that this is a thin layer of hardened resistant rock. It's most likely to be a seal. Right. Refer to A and B. Showing landforms resulting from igneous formations. We have the Power Rock in Western Cape, and we have Matopo rocks, which is the mother and child balancing rocks in Zimbabwe, in Matabeleland, to be specific. Right. Those two features are going to be our features of reference to answer the questions. Identify landforms A and B. Right, our landform A, this is a granite dome. And these are granitic toes. Right. Describe one characteristics of the rock from which the above landform develops. Which kind of rocks do those landforms develop from? They develop from massive igneous. Those rocks of volcanic origin, which has massive igneous. Or you can say they are hardened resistant. Rocks, or you can say they are rocks of volcanic origin, or you can say they are intrusive rocks in nature. Explain why these types of landforms are only found in certain areas in South Africa. Why are they only found in certain areas? For the reason being, because they are of volcanic origin. Because they are of volcanic origin, not all areas in South Africa experienced intrusive volcanicity. That's the reason. Because these rocks come from volcanic activity, it implies that they can only be found in certain areas that were exposed to volcanicity. And in that matter, it was intrusive. So in areas where there was no volcanic activity, we don't expect to find those landforms. There's no justification for their existence in those areas. Right. Moving on to the next question. Evaluate the economic importance of these landscapes. Why are they important economically? Right. We can talk of the importance in terms of tourism. They can be used for tourist purposes, people coming to tour, and also they are important sightseeing, or they are scenic. Important for activities. like rock climbing, hiking. All these activities, when they are done, they contribute income to the society. If we have tourists, we have people who come for sightseeing, they contribute to income. If we have activities like rock climbing, they also contribute to the income of the um, economy. Right, then the last question, it says, in a paragraph of mostly 8 lines, explain the formation of landform B. Explain the formation of granitic tores. How do they form? Right, I'll try to simplify the formational process. Right, number one, what happens is for them to form, there is intrusive volcanicity. And what happens after there's volcanicity, intrusive volcanicity, the rocks cool, and develop cracks. As the rocks cool inside, they develop cracks. And what is going to happen? Water seeps into cracks. And it causes chemical weathering. And what is going to happen? The joints are going to widen, or the cracks, because of chemical weathering. The rocks will break down. If it was one core rock with some cracks, then they're going to break down. As they break down, they form distinct shapes. They become rounded, or what we call the core stones. And what is going to happen? Landform is exposed over time by erosion. So basically, that is how they form. Starting from volcanicity, the cooling process of the rocks inside the Earth's crust results in formation of cracks, and those cracks are going to be affected by the water which seeps in. And as the water seeps in those cracks, it causes chemical weathering. And because of chemical weathering, the cracks or the joints, they widen, further breaking the rocks. And the rocks will gradually form into distinct shapes, mostly rounded shapes, which we call the core stones. And apparently the landform is exposed by erosional processes. Right, moving on to the next question. Next question is question number 2.4. Right, the 2.4 is based on features of the Karoo landscape. Right, name the landforms A, B, and C, respectively. Right, we want to name those landforms as shown there. Right, our landform A is wider than its height. It's a mesa. Our landform B has got a rounded top. It's a conical hill. Our landform C is narrower than its height. It's a butte. So those are the three landforms according to the labeling that is required. Draw a fully labeled symbol freehand sketch through the flat-topped hill at A to illustrate the four slope elements, or labeled 1 to 4. Right, when you're drawing this, whichever way you're going to draw it, I will draw it facing the opposite side. We want to draw this part to show these elements here. The slope elements that we have, starting from the top, right, we have the hard and resistant rock cap here, and then the softer rocks. So what is going to happen is, from here, we have a sloping scale like this. Then going to the bottom, it's flat. So if we try to check, our number 4 is somewhere here, which is the crest. And our number 3 is pointing somewhere here, which is the cliff. And then this is our number 3. Our number 2 is somewhere there, which is our talus slope. Then our number 1, which is our pediment. So basically, we're supposed to draw something with this shape. It must have a highline point, and then from there, an almost vertical slope. Then the slope angle must decline gradually going down and must be flat as we go to the bottom of the slope. Those are the slope elements that are required there. Right, explain the formation of feature B. Right, feature B, how does it form? Or feature B, we said it's a conical hill. So what happens here when you explain it simply. I will try to use an illustration. Right, let's start with this. Let's say we are starting from here. This is our mesa. There is scarp retreat, which is going to happen. Like that. Which means our landform is going to be eroded, and the cape rock is going to be eroded also from the top. If the cape rock is eroded, it automatically means the softer rock below is also going to be eroded, because it's the one that protects the bottom layers. So once this happens, it means our landform remaining is this one here. And the process continues until this cape rock is finished. The cape rock will get finished, and we are now having only the softer rocks. And the softer rocks are going to form a shape like that because they are easily eroded. They cannot have a flat top. So after that, we are going to have a landform which has got a conical shape on top, like the one which is illustrated on feature B. That is how a conical hill develops. It starts from a landform with a horizontal cape rock. The cape rock gradually gets eroded. It gets weathered and eroded, and the softer rocks are also eroded until the cape rock gets finished. As it gets finished, we remain with softer rock, softer layers of rock. Then those softer layers of rock will now have a conical top that gives us a conical hill. Right. Then the last question, it says scarp retreat or scarp recession, also known as backwesting, plays an important role in the development of these landforms. Explain the process of scarp retreat. Like what I've been mentioning there, I'll make an illustration. Scarp retreat happens like this. We have a wider landform with a rock cap and goes down. With the scarp retreat, we are saying the cape rock is going to be eroded, weathered and eroded. Let's say it has been weathered until this point. The slope angle does not change. It maintains. And again, if the process happens, the cape rock again is eroded, is weathered and eroded. The slope angle doesn't change. The landform maintains the landscape slope. So apparently, you are seeing if it is happening from this side and is happening from that side, it means the width of the landform is gradually decreasing. And at the end, we'll end up having this cape rock getting finished, and we now have a conical hill. So we are saying valleys, they widen. Valleys widen by scarp retreat. And that scarp retreat is caused by lateral erosion. Lateral or sideway erosion and mass movement. Then it reduces the plateau. We are starting from a plateau, it gets reduced to a mesa. And from mesas, they are reduced to butts. And from a butt, we apparently have a conical hill until we get a plane. So that is how the process happens. It widens the valleys of the landscapes and is caused by lateral erosion, which is sideway erosion. And it is supported by mass wasting processes and mass movement. And as a result, the landform gradually reduces in its width until it gets finished. Right, we move on to the next question, number 2.5, which is on mass movements. State the type of mass movement that occurred in Himachal Pradesh. That is indicated here. Intense long rainfall triggered multiple landslides. So it's a landslide, that is the mass movement. It's a landslide. Name the main causes of this type of mass movement. What was the main cause of that one? If we check here, we also see that intense prolonged rainfall was the cause. Was caused by prolonged rainfall. Right, moving on, identify three consequences of this type of movement to critical infrastructure. We just extract it here. One, the consequences to critical infrastructure. Right, if we check here on infrastructure, we are seeing the highway being washed away. It's one impact. Then we're also seeing the road being blocked here. It's another impact. And also if we check, we see a road which is carved in here. It's also another impact on infrastructure. And also if we check, again, there's a blocked road which is indicated. And also we see there are mudslides inside this particular built up area. And also a washed away highway. So these are critical infrastructure. We are seeing the highway being washed away, and we're also seeing this major road being blocked. We are also seeing the highway section being washed away. We are also seeing the road which is carved in on that part of the slope there. So basically, those are some of the impacts that we can see from the extract. Right, then if we check on question, if we check on the next question, what happens? We're looking at the type of mass movement. We said it was caused by prolonged rainfall. And the three consequences, we've highlighted them from the extract. So the next question is saying, explain why this type of mass movement was fast. Why was the landslide fast? Right. We can attribute the speed of the landslide to the heavy rain. Right. What is the impact of the heavy rainfall? How did it facilitate the heavy rainfall? It added weight to the moisture. So the rainfall added weight to the debris because of moisture. So when there's moisture in the soil material, it can easily move faster because of the weight. It's now heavier because of the added weight, and then it can move faster down the slope. And also we can argue that there was lubricating moisture. The presence of lubricating moisture will also facilitate a smooth movement of the eroded material, and then it can move faster. And also we can talk of the gradient of the slope. Where it's steep sloping, it facilitates faster movement. So basically, why the speed of the movement was faster is because of some of those reasons. The nature of the gradient, the steep sloping landscape, it moves faster because of the nature of the steepness. And also, presence of lubricating moisture will facilitate the movement of the material. Right. Then we move on to the last question. Last question is saying, why you think people should be made aware of the consequences of mass movement? Why should we let people know about the dangers of mass movement? Right. Number one, we need to avoid. We help avoid disasters. If people are made aware of the negative implications of the mass movements, then we can assist in disaster prevention. And also we can argue that it will help to encourage people it will help to encourage people prevent the disasters. Or we can say, for example, people can take initiative for reforestation on slopes. It's a measure that can be taken into place because of people knowing the dangers of such disasters. And also, we can also argue that so that people can reinforce slopes. Control mass movements. Yes, it's a measure also that people can take, reinforcing or building of retaining walls. People can only effectively do that when they know the dangers of the mass movement processes. And also we can talk of resilience building. We build resilience amongst the people. If communities are educated, we're talking of educated communities here, they know the consequences, are better equipped. If a person is made to know the dangers of a given natural disaster, they become more equipped. towards the disaster. And also we can talk of community planning. Enhance community planning. People can work together as a community to find ways of how they can try to minimize the dangers of the mass movement. And also, lastly, we can talk of risk understanding. For risk understanding, people living in or visiting prone to disasters. So it's for risk understanding. People must know the risk associated with whether they are visiting a place or they are living in a particular place. They must understand the risk of their place of residence. They must know the dangers associated with the areas where they are staying or areas that they must be visiting. It's key, it's important that people are made aware of such dangers or such consequences so that whatever they are doing, they know that there's a risk associated with the places where they are staying or with the places where they intend to visit. Right. That was the last question of the geomorphology or the theory section. Then we move on to our Memo question. The Memo question is based on the map on Franstrop, which is Vredendal. Right. That is map information. Vredendal is a town in northern Oliphant River Valley in Western Cape Province of South Africa. Wherever the information there, you can read it through. Right. The first question is saying the province located west of Vredendal is right. If I take you to the map information, we are seeing that this Vredendal is here. It's located here in the Western Cape province. This is our Western Cape, and this is the Northern Cape, and this is or Eastern Cape. Right. So we want a province to the west of Vredendal, the province which is to the west of Vredendal. Automatically, there's no province which is to the west here because we see the west coast, the Western Cape is on the western coast. This is the Atlantic Ocean. So it being in the Western Cape province, to the west is this side. So automatically, we don't have a province here. The only province which are neighboring the Western Cape is Northern Cape to the east and Eastern Cape to the east. So based on that response, we can only give the very same province as the response. The very same province where we find it is the very same province which is to the west of that Vredendal. So since it's found in the Western Cape, that is the province to the west of it. Right. The topographical map or orthophoto map has a small scale. When we talk of scales of maps, we talk of large scale and small scale map. A small scale map covers a wide area but shows less detail, while a large scale covers a small area and shows more detail. So a topographical map is a small scale, 1 to 50,000, compared to 1 to 10,000, it's a large scale map. Then the human-made feature located at 31, 38, 24 and 18, 31, 19. Right, if we try to check from our map, this is our map. We are looking at coordinates of latitude, that is 31 degrees, 38 and 24, which means we are in this block here of latitude. We are in this block here, along this line. That is where we are picking along this line. That is where we are picking our line of latitude. But we need to be worried about the second line, which is 24. If you are to estimate the midpoint of this block, because this block is starting from here and is ending here on latitude. So if we try to estimate the midpoint, where we find 30 seconds is somewhere here, the midpoint. If we draw a horizontal line along that point, that will give us the 30. We are estimating. Let me try to draw it straight. If we are estimating using estimation, if we draw a horizontal line around the midpoint of that block, that gives us 30 minutes of latitude. Then our longitude is 1831. So, which means our line of longitude is extending to the next block, because this is 1830, the first line. This is 1831. So, which means our block of concern, we must continue with this line, the assumed 30 minutes line, and we are saying this is our reference point of longitude. So our block is this block here with this northwest corner. By mere looking at this one, we want to estimate the value of longitude. Our value of longitude in seconds is 19. It's 1831 and 19 seconds. So if we try to estimate the 30, I think our 30 in terms of longitude can come along this line by estimation. So we want 19. 19 is slightly after the quarter point, which is somewhere here. And here we were saying we're estimating 30 for latitude, but we want 24, which means we must move slightly to the top here to get 24. So where these two are meeting, they're meeting somewhere here by estimation. This feature here, as we are seeing it, it's a symmetry. By mere estimation, we are not using calculations, we are just estimating. But if we have estimated correctly, we can see that these 2 points are meeting on a symmetry. So we can say our correct response is a symmetry. So symmetry. Right, to move on to the next question. Calculate the area of the cultivated land in block D5 in square meters. Right, we go to our map, we want to calculate the area in block D5 of the cultivated D at number 5. We want this feature here, the cultivated land. This marks our length of the area, and this marks our width of the area. This is a polygon or an area feature. So we want to determine the area of that. According to my measurements, if I were accurate enough, I got a 2.2 for the width, and for the length, for the width, I got 0.8 centimeters. So given those two measurements, we use those two measurements to calculate the area. So let's do our calculations on the question paper. So for the length, got 2.2. This is from a topographic map. Our map scale is 1:50,000. Convert to meters, we multiply by 500 meters. This is for length. And for our breadth is 0.8. Again, we multiply by the map scale of 500 meters. Right, what are we going to get here? If we multiply 2.2 by 1,000, we get 1,000 100 meters. Then we multiply 0.8 by 500. It gives us 400 meters. So our area, we are saying 1,100 meters times 400 meters, which is going to give us 440,000 square meters. That's our calculation for that area. Right, calculate the magnetic bearing from the wind pump in block A5, the wind pump in block B5, if the current magnetic declination is 2388 west of true north. Right, we go to our map and try to identify the two features. We want a wind pump in block A5. Right, if we go to block A5, we can see we have a wind pump here and another wind pump in block B5 is here. So what we want is the bearing from this one to this one. We want to calculate the angle from this to this. So what we do there is when you're doing your calculations, you draw your north-south line, which is almost along assuming this is a straight line and it's parallel to the longitude line, right? You draw your line straight, and from the feature, you draw a straight line, again, joining or connecting to the feature that we want to determine. Straight line like that. Then, after doing this, we know that this is our true north direction. Whenever we draw a vertical line parallel to our lines of longitude, we have identified our true north direction. So using that true north direction, then we can now be able to ascertain our bearing. Remember, our bearing is measured in a clockwise, true bearing in a clockwise direction from the true north to the line connecting the two features. So you place your protractor in such a way that your zero reading is on the true north, and you check on your markings of the protractor where this line crosses the edge of your protractor. If you calculate correctly, I think you can get something around 163 degrees, somewhere there. Then with that value, we want to calculate magnetic bearing. Our magnetic bearing, we know, is true bearing plus magnetic declination. That information of magnetic declination is already provided. So we just want to use the true bearing information. So we are now saying our magnetic bearing is equal to 163 degrees plus magnetic declination 23 degrees and 38 minutes. So if you add those two, they are going to give you 186 degrees and 38 minutes. So that qualifies to be our correct answer. It will partly depend with your accuracy of determining the true bearing from your protractor. Why is it important to calculate the current magnetic bearing? Right, the current magnetic is important. Why? Because the direction of the true of the angle is always changing. Angle is always changing. Remember, we have mean annual change. So because of the mean annual change, we always have the angle changing. So if we don't accommodate the effect that it's always changing, it will automatically also mean that we might be able to fail to get the accurate direction. So to get get accurate direction. Or we can say accurate navigation. It's stemming from the fact that it's always changing, and therefore, if we don't calculate the current, it means we might fail to navigate effectively because it is changing. If we use the old one, it is going to give us the wrong direction. Since it's changing, we cannot use for a particular year. We have to use for our current year so that we access and get the correct direction of where we want to navigate to. Right. Moving on to the next question. The contour interval on the orthophoto map. This one here, it doesn't change. It's always the same. If we refer to our map, we want the contour interval on the orthophoto map. We go to our orthophoto map, the information is here. Contour interval, 5 meters in Afrikaans, so provided there. So it's common information that our contour interval is 5 meters. Refer to block B4 in the orthophoto. B4 in the orthophoto map and block B3 in the topographical map. So we want B4 and B3. B4 on orthophoto and B3. Right, B4 in orthophoto, we are seeing that block B, 1, 2, 3, 4 is this feature here. Right, that is block B4 on the orthophoto, and on the topographic, the same feature is found in block B3. B3, our block B3, B1, B2, B3 is also here. This is the same feature. So the question is saying, identify the feature. The feature we've seen it is the sewage works. That's the feature. Why does the feature in question 322 appear larger on the orthophoto? It is appearing larger because orthophoto is a large scale. In other words, you are saying it was enlarged 5 times bigger than on topographic. Because of the differences in scale, we are seeing that the orthophoto is a scale of 1:10,000. And this one, the topographic, is 1:50,000. So if you are comparing these two scales, we are seeing that it's actually, this one is actually 5 times bigger than this one. 1:10,000 is 5 times bigger. So features which are shown on the orthophoto map, they will be 5 times bigger than they appear on the topographic map because of the differences in scale. Right. Number 232. The town planners argued that the feature 1 in question 322 is ideally located or is well located. Yes, it's ideally located. Mention one disadvantage of people living near feature 1. If people are living near the sewage works, what is going to happen? They're going to have problems of smell, or we're going to talk of the bad odor, or we can talk of air pollution. Or can talk of water pollution can be possible. Right. So that's the disadvantage of living near that feature. Indicate which settlement X or Y will be negatively affected. Right? If we check the the settlements X and Y, we want to identify the one which is most likely to be affected. Right? Between the two, we want to identify the one which will be negatively impacted. Right? If we check our X, we find that our X is somewhere here. And where is our Y? Our Y is here. Right? For the reason of distance, you are seeing where X is located and also where Y is located. Arguing based on the reasons, we justify that X is the one which is most affected because it's much nearer to the feature. So X and Y, the one that will be affected is settlement X. What can municipality do to assist the inhabitants of the settlement identified in the previous question? We have seen that those people are likely to face the problems of air pollution, the problems of likely water pollution. So what can be done to try and assist those people, right? I'll indicate the response for C here. Right, what can be done then? We can try to educate the community. Educate the community. On health issues. It's important to equip the people with the knowledge on health issues so that they take preventive and corrective measures. And also, we can also try to assist with odor management. Either e.g. through the use of sprays. We can do odor management, e.g., for example, using sprays, or we can enhance activities like covering the sewage works. Like mainly when it's not operational during the night, we can cover the sewage works so that the smell cannot affect the people. We can also provide health needs, provide for health needs. Health needs, for example, if people need masks or if they need medication, that can be also another measure. And maybe lastly, you can try to allocate land away from the sewage works. Right? Those are suggestions that can be implemented, but are not limited only to those ones. Then we move on to the last question, number 3.2.4. So part A says identify the river at M. Identify why does the feature appear larger, right? Right, we want to look at the question number 2.4. It says identify a river at M. Our M you can see here, it's here. And the name of the river is shown along the river here. So that river is named the Olifants River. This one is the Olifants River, is labeled here. And the next question is saying, why is the river at M called perennial? Right, if we check the nature of our rivers on the map here, we have non-perennial and perennial rivers. Like if we check example, there are some maps, some rivers, like if we check rivers like the one which is here, compared to this one here. So perennial rivers, they are shown by a solid blue line. While it's non-perennial, they are shown by a broken like this. So this one is non-perennial. Wherever you see a broken blue line, it shows a non-perennial river, but a solid one shows a perennial river. So for that reason, this is a solid line, a solid blue line, which is shown to represent that river. It means it's a perennial river. It has a solid blue line. Right. Moving on to the next question. What is raster data? According to our sets of data, we have raster and vector data. Raster data is data which is stored in grid cells or in pixels. That is raster data. So it's geographical data which is stored in grid cells or in pixels. Then a topographic or orthophoto is a representation of raster data. It's an orthophoto map. Or topographic is a vector data. Right, with reference to block C4 and C5 on the topographic map, identify two transport infrastructure data layers that were considered by GIS specialists when developing the topographic map. Right, we are referring to block C4 and C5. We want to look at transport infrastructural data layers. Right, in block C4 and C5 on our map, right, what we want here is to check in these blocks. Right, we can see that in terms of transport layers, we have this, and we also have this. So we have railways, and we also have roads. So those are the two data layers in those blocks. We have railways and we have the roads in those two layers. In those two blocks, those were the infrastructural data layers. Refer to image A and B, which are images of a settlement located in block A2 on the orthophoto. Which image A or B illustrate a high resolution? High resolution is B. For that reason, why are we saying it's high resolution? Is because it's clearer. It's more clearer compared to that one, to the first one. And you can say it has more detail. Or You can say it has smaller pixels. Yes, many pixels. So the difference between a low resolution and a high resolution is a low resolution is you can't clearly see the features there. It shows less detail, cannot see clearly. It's less clearer, it's blurry. And the implication is it has bigger pixels. Like if you zoom an image, it will end up not being clear because you're enlarging the pixels. And remember, the pixels, these are small squares that make up an image. So if you enlarge those small squares, it will end up being blurry or less visible and giving less detail. But if it's a high resolution, it's a clearer, it has more detail. And also in terms of the size of pixels, they are smaller. The smaller the size of the pixel, the more clearer the image is. And if you check also on the number of pixels, if they are larger, it means we are going to have a smaller number of pixels in the image. And if they are small, we're going to have a large number of pixels in the image. So if the pixels are smaller, it is going to give us a clearer image or a high resolution image. That is why we're justifying that B is a high resolution image because it's more clearer. We can actually see the details of the place. Right. Remote sensing can be very useful to the people of Redindal. Explain how remote sensing can assist in managing environmental issues faced by the people in the settlement. 2 in block A2 on the orthophoto. Right, if we check on that orthophoto, try to check on area 2, we can see that these people at 2 um, we want to identify and try to see how we can use remote sensing to deal with the problems that they are likely to face. Typical problems that they can face there is the problem that is caused by the sewage works, which is to the extreme southeast of their settlement. Right. So what can be done to, using remote sensing? Try and find solutions to typical problems caused by effect of the sewage works on their lives. Right. We can talk of the collection of data, or monitoring. You can use remote sensing to collect data for monitoring the situation, or you can use remote sensing for air quality control. Air quality monitoring, rather, so that we can implement control measures. We start by monitoring. Air quality monitoring. Since it is close to the sewage works, we need to constantly monitor the air quality and also need to collect data for monitoring purposes. Right. So basically, that is how they can benefit from remote sensing in that particular area. And given that question, it was the last question of our discussion for the set of questions that we were supposed to address. So for that reason, this brings us to the end of our discussion session on grade 11 geography. I hope it is going to assist you in your studies and also in preparation for your exams to follow. Right. With that being said and done, it brings us to the end of our session. Thank you for watching your Western Geography.